Welcome back to the deep dive.
Yeah.
Today, I want to start by putting you in a very specific headspace. So just imagine you're driving.
Okay.
It's late at night, maybe it's raining a little bit, you're on the highway, you're miles from home, and you glance down at the dashboard.
The dreaded glance.
Exactly. You look at the range indicator, and you see that number dropping way faster than you expected. You're doing the mental math in your head.
Distance to home versus kilometers remaining in the battery.
Right. And suddenly your chest gets a little tight, your palms get a little sweaty on the steering wheel.
Range anxiety is
Yeah.
the absolute universal electric vehicle experience.
It really is the defining anxiety of modern driving. We are all completely obsessed with it. And because we're obsessed with it, we tend to obsess over the big shiny numbers on the spec sheet, right? We look at a car and we say, how big is the battery pack? Is it 100 kilowatt hours? Is it solid state?
We look at the aerodynamics, the weight of the chassis, which makes total sense. I mean, those are the headline acts.
Right, they sell the cars. But today, we are going to look under the hood. And I don't just mean popping the latch and staring at that big plastic cover. I mean, we are going to look way, way under the hood into the microscopic invisible wars that are actually determining whether that range counter drops fast or slow.
It's a genuinely fascinating place to be. Usually when people talk about electric vehicles, they focus entirely on the energy storage. But if you talk to the engineers, the people actually designing the systems that keep these cars running on a daily basis, the real battle isn't just about how much energy you can carry. It's about how you manage the enemy of efficiency.
And who is the enemy here?
Heat.
Heat, the silent killer of electronics.
And the silent killer of range. So the deep dive today is centered on a very specific piece of technology that addresses exactly this. We're looking at a presentation from a company called EQIO.
Which is a brand under the massive Saint-Gobain group.
Right. And the source material we're working from is a webinar titled, let me get this right, Reducing xEV Energy Use by 58%, the thermal management valve that redefines efficiency. It was presented by Christian Ellis, their product engineering manager, back in December 2025.
And the central mystery that we are going to unpack today is honestly kind of geometry-based. It's about how changing a single tiny component from a circle, which has been the industry standard for literally decades, to a triangle, can suddenly unlock this massive leap in efficiency.
It sounds like a riddle, doesn't it? Like, when is a triangle better than a circle?
It does. It sounds like something a Zen master would ask you before hitting you with a stick. The wheel is round, but the efficiency is triangular.
Exactly.
But before we get to the Zen koans of engineering, we really have to understand the players here. Because you mentioned EQIO is part of Saint-Gobain. And I feel like Saint-Gobain is one of those companies that everyone has vaguely heard of, but no one really knows just how big they actually are.
Oh, they are a true industrial giant. We are not talking about a garage startup here. Saint-Gobain has a 350-year history.
Wait, I have to stop you on the name. Because when we talk about cutting-edge car parts, I picture a sterile factory in Detroit or maybe a massive tech park in Shenzhen. But you're talking about Saint-Gobain. Didn't they make glass, like the mirrors for the Palace of Versailles?
That is exactly them.
Yeah.
Louis XIV, the Hall of Mirrors, 1665. That is how far back this corporate DNA goes.
Okay, so we have a company that was literally founded by a French king to make luxury mirrors for aristocrats, and now you're telling me they hold the key to the future of electric vehicles? That feels like a massive stretch. Like, what is the connective tissue there? How do you go from Baroque mirrors to EV thermal management?
It does sound like a huge leap when you put it that way. But think about what glass making actually is at its core. It isn't just, blowing hot air into a tube. It's high-temperature material science. It's fundamentally about understanding how atoms structure themselves under extreme heat and extreme pressure. And over 3.5 centuries, that expertise just evolved. They moved from glass to ceramics, from ceramics to crystals, and eventually to high-performance polymers.
So the thread connecting Louis XIV to a Tesla Model Y is basically manipulating atoms.
Precisely. The connective tissue is material science. They are absolute masters of the microscopic structure of matter. And they've been doing it longer than almost anyone else on the planet.
Okay, so they've been manipulating atoms for 350 years. I guess that gives them a bit of a head start compared to, a startup that launched on Kickstarter last week.
Just a little bit, yeah.
Okay.
And that scale is really critical here. We aren't talking about a niche supplier. To put it in perspective, in 2024, they did 46.6 billion euros in sales.
Wow.
They operate in 76 countries with over 160,000 employees.
I can't even visualize that many people. That's the population of a decent-sized city just making materials.
It is. And for you listening, this isn't just corporate trivia. It actually matters because of a concept called risk. If you are Ford or Toyota or Volkswagen, and you are betting your entire electric future on a brand new cooling system, you absolutely cannot take a flyer on a company that might go bankrupt next Tuesday.
Right. You're building millions of cars. If the supplier goes under, your assembly line literally stops.
Exactly. You need a partner who can survive a recession, who has supply chains in 76 countries. EQIO calls it their global partner, local doorstep philosophy.
Which translates to, we are everywhere you need us to be.
Right. They have 8 global R&D centers. So if a car maker in Germany has a problem on the line, they don't have to wait for an engineer in Japan to wake up to fix it. They have local support immediately. That safety net is literally part of the product. But let's pivot to the problem they are actually trying to solve. Why do we even need a new valve? What's wrong with the cars we're driving right now?
Well, as a driver, I can tell you the pain points firsthand. We touched on range anxiety right at the top, but it's also the charging time. The source material highlights the specific gap. A standard gas car gets, what, around 1,200 kilometers on a full tank if you're driving efficiently?
Around 1,207 kilometers is the benchmark they use in the presentation, yes. That is the gold standard of convenience we are all used to.
Right, and EVs are still lagging behind that at around 830 kilometers for the really top-tier models. That's a significant difference if you're planning a massive road trip. You are stopping more often.
You are. And the other side of that exact coin is how long those stops actually take. The entire industry's target for high-power charging HPC is to get down to a 9-minute charge.
9 minutes. Man, that would be a game changer. That's basically a bathroom break and grabbing a coffee. You wouldn't even finish listening to this deep dive.
Exactly. But here's the massive catch. You cannot just pump electricity into a battery that fast without severe consequences. Think about the physics of energy transfer. When you push that much energy that quickly into a chemical storage system, you generate massive amounts of waste heat.
Is it like, imagine trying to fill a water balloon with a fire hose.
That is a perfect visual. The friction of the water aggressively entering the balloon creates pressure and heat. In a battery, it's internal resistance. If you don't manage that heat instantly, you destroy the battery. Or worse, it catches fire.
And that is where the thermal management system comes in.
It is the ultimate bottleneck. The source material calls it a multi-front battle because it's not just the battery you have to worry about anymore. In a modern EV, you have to cool the high-voltage battery to keep it safe and efficient, but you also have to cool the electric motor.
Wait, the motor gets that hot too? I thought electric motors were super efficient.
They are, but they're still spinning at thousands and thousands of RPMs. They generate incredible heat. And you also have to cool the power electronics, specifically the inverter that changes DC power from the battery to AC power for the motor. That's the brain of the operation, and silicon chips absolutely hate heat.
Right?
And don't forget, you still have to keep the cabin comfortable for the actual humans sitting inside the car.
Okay, so you have all these different systems, and I imagine they all need completely different temperatures, right? Like the battery probably likes it cooler than the spinning motor.
Correct. It is a highly complex dance of fluids. The battery might need to be kept at exactly 25 degrees Celsius. The motor might be totally fine at 60 degrees. The power electronics might need 40 degrees. So you are constantly moving coolant around, mixing it, diverting it from one loop to another.
It honestly sounds like a plumbing nightmare.
It is a hydraulic logic puzzle.
No.
And the component that controls that entire flow, the traffic cop of the cooling system, is the valve.
Okay, so the valve is the unsung hero here.
Or the villain, depending on how well it's designed. These valves have to handle full flow control, meaning they aren't just an on or off switch. They have to smoothly regulate the exact amount of liquid passing through. They need to be highly chemically resistant to the coolant, which can be pretty harsh stuff. They have to handle extreme hot and cold cycles day in and day out. And crucially, they need to be cheap and light.
That is a tall order. It has to be fast, strong, cheap, light, and smart.
Exactly. And that is where the geometry of efficiency really comes into play. But before we build the actual valve, we really have to look at what it's made of. The source material emphasizes that EQIO starts their optimization right at the ceiling level.
Right, the bricks before you build the house.
Exactly. They have a proprietary material called Meldon.
Meldon. It sounds like something straight out of a fantasy novel. You know, like the legendary shield of Meldon.
It's almost as tough, honestly. It's not just a single basic plastic. It's what they call a material pyramid.
Hmm.
At the very top of this pyramid, you have high-performance polymers like PEEK, PPS, and PI.
Okay, stop there for a second. Peak, PPS. I feel like I'm reading a chemistry periodic table. What actually are these things?
Right, let's break it down. PEEK stands for polyether ether ketone. It is an organic thermoplastic polymer, but what you really need to know is that it's incredibly strong, incredibly heat resistant, and, frankly, very expensive. It's used in aerospace, it's used in medical implants.
Okay, so this is definitely not the cheap plastic used to make a disposable soda bottle.
Far from it. This is super plastic. But the thing about Meldon is that it isn't just the base polymer, that's just the foundation. They mix in specific additives and fillers to deeply customize it.
So it's like baking a cake. You change the flour, maybe add some chocolate chips, throw in some nuts, depending on what you want the final texture to be.
That's a great analogy. The flour is the PEEK or the PPS base. The chocolate chips might be carbon fiber to add stiffness. The nuts might be graphite or PTFE to add lubrication. They can tweak the specific recipe for friction, for stiffness, or for chemical resistance. They actually have over 100 different options available.
Wow. One thing that really stood out to me in the source material when reading about this was the environmental angle, because we hear a lot about PFAS these days, the forever chemical.
Oh, it's a massive topic in the automotive industry right now.
Hmm.
Regulations are tightening rapidly, especially in Europe and across the U.S. Manufacturers are basically scrambling to find PFAS-free alternatives because the writing is absolutely on the wall.
And EQIO is ahead of the curve here.
They are. They have over 40 PFAS-free formulas ready to go right now. But here's the truly surprising fact, and this is where the material engineering gets really cool. Usually, when you switch to an eco-friendly alternative in manufacturing, you just expect a performance hit.
Right, it's the paper straw effect. It's better for the sea turtles, but it dissolves in your iced coffee after 10 minutes and tastes like wet cardboard. You just kind of accept the suffering for the greater good.
Exactly. We have all been conditioned to think that green inherently equals less effective. But in this specific case, the source notes that their PFAS-free version, specifically the Meldon EO-PAE-KPS blend, actually performs better than the traditional stuff that uses PTFE.
Wait, better?
Noticeably better wear rates and better friction coefficients.
How is that even physically possible? Isn't PTFE, which is basically Teflon, right? It's supposed to be the slipperiest stuff on Earth?
It is extremely slippery. But tribology, which is the study of wear and friction, is super complex. What EQIO found is that their specific proprietary blend creates what's called a transfer film. As the valve moves back and forth, microscopic bits of the Meldon material literally smear onto the mating surface, creating this perfectly smooth, self-lubricating layer. It essentially heals itself as it wears down.
That is wild. So going green didn't require a compromise at all. It actually improved the lifespan of the product. That's
Yeah.
basically the holy grail of sustainable engineering.
It really is. So we have the material down. We have this high-tech, low-friction, incredibly durable polymer. Now let's talk about the shape, because this is the absolute core of the episode, the triangle valve.
Okay, set the scene for us here. What is the current standard? If I go out and open up a brand new Tesla or a BMW right now and somehow locate the cooling valve, what does it look like?
You're almost certainly looking at a ball valve. Imagine a solid sphere with a tunnel drilled right through the middle of it. To open the valve, a motor rotates the sphere so the tunnel lines up perfectly with the pipe. To close it, the motor rotates at 90 degrees so the solid wall of the sphere blocks the pipe.
Simple enough. I mean, it works for the shutoff valve on my garden hose.
It works, absolutely, but it has severe limitations at scale. The source material references a direct benchmark they did against a cooling valve from a, quote, German luxury OEM. They don't name names, but we can safely assume it's a very high-end vehicle.
And what did they find when they took it apart?
Extreme complexity. The competitor valve had 10 distinct parts. It was this complicated mix of metal, rubber, ceramic, and plastic, all basically shoved together into one unit.
10 parts for one single valve. That sounds like a lot of potential failure points.
It is. And it's heavy. And it's really expensive to assemble on a line. Now, compare that directly to EQIO's approach. They looked at that heavy 10-part ball valve and said, we can do this with radical simplicity. Their new triangle valve uses only 4 to 6 parts.
4 to 6 parts. That's basically cutting the mechanical complexity in half.
Easily. And it's primarily made of plastic, thanks to that Meldon material we just talked about, which brings the total weight down to just 145 grams.
145 grams. That is incredibly light. That's like the weight of a smartphone. But the shape, why a triangle? How does making it triangular actually work?
Well, this is the real aha moment of the whole design. Think about the ball valve again. To properly seal a sphere so water doesn't leak out, you need sealing material wrapping entirely around it. The source mentions that a traditional ball valve has 3 distinct sealing points around its circumference.
Okay, visualize this with me. I have a ball, I have a tunnel through it. When the tunnel lines up, water flows. When I turn the ball, it blocks the water. Why are the seals a problem?
Because of the physics of turning that ball under pressure. To keep it completely watertight, you need those seals, usually rubber or plastic rings, pressing incredibly hard against the surface of the ball at all times.
Right, otherwise coolant drips out and you ruin the car.
Exactly. So
Yeah.
you have this sphere, and it is being hugged incredibly tightly by these seals. Now imagine trying to rotate it. There is immense friction everywhere. And where is that friction located? It's on the outside surface of the ball.
Right on the equator.
On the equator, exactly. Now, do you remember your high school physics? The formula for torque?
Vaguely. It's force times distance, right?
Bang on. Torque, which we'll call m, is force times distance, or radius. To turn that valve, you need to overcome the friction force. But because the friction is happening at the equator, the absolute widest part of the ball, your distance variable, the radius, is very large. You are fighting a massive lever arm.
Oh, I see. It's like trying to stop a spinning bicycle wheel by grabbing the tire itself versus grabbing the little hub in the center. The tire has way more leverage against your hand.
That is exactly it. In a ball valve, the friction has all the leverage.
Right.
So to overcome that, you need a big, heavy, strong electric motor just to crank this valve open and closed.
And a big motor means?
More weight, more cost, and most importantly, more power consumption. You are literally wasting precious battery life just to open and close the plumbing.
Okay, so the ball valve is basically a friction trap. It's constantly fighting itself. So what did EQIO do to fix it? Did they just use better lubrication?
No, they didn't just try to optimize a flawed concept. They stopped polishing the cannonball. They changed the geometry entirely. They asked the fundamental question, why does it even have to be a sphere?
Let's try a triangle.
Exactly. Now visualize the EQIO triangle valve. It is a planar structure. It's completely flat. It is not a big, bulky 3D sphere. And the sealing point, it's just one single point located right at the drive center.
Wait, so instead of rubbing on the far outside edge like the bicycle tire, it's pivoting directly from the center hub.
Precisely. The lever arm, the friction radius in the physics equation is absolutely tiny compared to the overall size of the valve. It's minuscule.
So the mass just completely changes.
It does. The torque required to turn this triangle valve drops off an absolute cliff because you have completely minimized the radius where the friction actually occurs.
Less rubbing at a smaller distance means way less energy needed to turn the valve.
And that brings us directly to the numbers from the presentation, and they are honestly staggering for a component level change.
Let's hit those numbers, because the title of the webinar was literally Reducing xEV Energy Use by 58%. Is that a real practical number?
It is real. And it's based specifically on the energy consumption required to actuate the valve. Because of that geometry change we just walked through, the triangle valve requires 58% less energy to open and close compared to the German luxury standard ball valve. That is a delta of 0.156 joules per actuation.
Okay, I'm going to play devil's advocate here for a second. 0.156 joules. That sounds microscopic. That's like, I don't know, the energy of a housefly landing on a sandwich. Why are we throwing a parade for a fraction of a single joule?
I love the housefly analogy, but you are missing the scale of the operation here. If you were just opening the valve once a day when you turn the car on, you'd be right. Who cares? But an EV thermal management system is practically a living, breathing thing. It is constantly, endlessly adjusting.
Because the driving conditions change every second.
Constantly. You accelerate hard onto the highway, massive heat spike in the motor. You brake for traffic regeneration, energy flows back to the battery, heat spike in the battery. You stop at a red light, cooling needs suddenly drop. You plug into a fast charger, extreme cooling demand. That valve isn't just sitting there in one position. It is dithering. It's making micro adjustments continuously to perfectly mix the hot and cold coolant loops.
So it's basically twitching all the time.
It is twitching thousands upon thousands of times per drive. Now multiply that housefly landing on a sandwich by 1,000,000 twitches. Suddenly, that parasitic electrical load really adds up and eats into your range. But there's a whole second layer to this 58% savings.
Which is what?
Reaction time. Because the triangle is so much lighter than a solid sphere, and because the friction is so incredibly low, it can move much faster. Specifically, the driving angle is reduced by 50%.
Okay, so because it's a triangle shape, not a full circle, the motor doesn't have to physically turn it as far to open the pipe.
Exactly. A traditional ball valve usually needs a full 90-degree turn to go from fully closed to fully open. The triangle valve cuts that driving angle completely in half, so you get from off to full cooling twice as fast.
And in a thermal runaway situation, or honestly even just a high-performance driving scenario, those milliseconds really matter.
They do. If you can inject cold coolant into the battery pack 2 seconds faster, that might literally be the difference between the battery staying in its safe Goldilocks zone or permanently degrading its chemistry. So that 58% energy saving is really nice for extending your range, but the mechanical speed it unlocks is critical for the long-term health of the battery.
That is fascinating. But what about the actual liquid flowing through it? Because I imagine if you stick a weird flat triangle shape into a round pipe, it might mess up the flow of the water. It seems a bit counterintuitive.
You would naturally think so. You'd think a flat plate intersecting a pipe would create crazy turbulence. But the fluid dynamics actually improve dramatically. The source cites a 45% lower pressure drop.
Pressure drop, unpack that term for us.
Think of pressure drop simply as resistance. If you are drinking a thick milkshake through a tiny, crushed-up straw, that is a high pressure drop. Your lungs, or in the car's case, the electric water pump, have to work really, really hard to move the liquid.
Okay, yeah, I can feel that headache already.
Right. But if you have a wide, perfectly smooth straw, that's a low pressure drop. The liquid just flows easily. A 45% lower pressure drop across this valve means the car's water pump doesn't have to work nearly as hard to push the heavy coolant through the entire system.
And if the pump doesn't have to work as hard?
It uses less electricity from the battery, which saves that battery capacity for what you actually bought the car for, driving.
So it's a double whammy of efficiency. The valve itself uses less power to physically move, and it makes the main water pump use less power to move the fluid.
Precisely. And it even performs noticeably better when it's actively mixing fluids. Often, these valves sit in what they call a 50-50 position, mixing hot liquid from one loop and cold liquid from another to get the exact perfect temperature. The planar triangle valve is significantly more efficient and causes less turbulence at this mixing stage than the spherical competitors.
It sounds almost too good to be true, honestly. Usually when you make something lighter and cheaper and simpler, it inherently becomes more fragile. Is this thing just going to snap in half after a week of driving over potholes?
That is exactly the robustness aspect that the source material covers in depth.
Yeah.
And surprisingly, the simplicity actually makes it much stronger.
Just fewer parts, fewer things to break?
That's a big part of it, yes. But also, the design has a really clever self-closing feature. Naturally, the internal pressure of the liquid and the specific shape of the triangle make it inherently want to stay in a safe, sealed position. Plus, there's the whole issue of tolerance and sensitivity.
Tolerance and sensitivity. That sounds like a bad piece of relationship advice. You know, you need more tolerance and sensitivity.
In relationship therapy, maybe, but in mechanical engineering, it's incredibly valuable. In mass manufacturing, absolutely nothing is perfect. Every single part has tiny microscopic variations from the mold. With a complex 10-part ball valve, if one internal part is slightly off spec, the whole thing might leak or jam entirely.
Because everything is just jammed in so incredibly tight to maintain that seal.
Right. Every part relies on the other parts being flawless. But the planar, flat triangle design is much more forgiving of these micro errors. The normal manufacturing variations simply don't ruin the efficiency or the seal. It is a fundamentally more stable, resilient design.
Okay, I really want to talk about how they actually engineered this shape, because they didn't just whittle it out of wood and test it in a sink, right? I mean, this is 2026.
No, absolutely not. This is the era of the digital twin.
Digital twins. I love this concept, but what does it actually mean in the context of a plastic valve?
EQIO used incredibly advanced computer simulations, specifically CFD, which is computational fluid dynamics, and FEM, which is finite element method. But the brilliant part is they combine them into something called FSI, fluid structure interaction.
Okay, that's a lot of acronyms, Sue. Break FSI down for me.
FSI is notoriously difficult to simulate properly. You are literally simulating the behavior of the liquid, the flowing coolant, and the solid, the plastic valve at the exact same time.
Why is that so hard for a computer to do?
Because they constantly affect each other in real time. Imagine a flag flapping in the wind. The wind physically moves the fabric of the flag. But the changing shape of the flag immediately alters how the wind flows around it, which then moves the flag differently. It's an endless feedback loop.
Oh, I see. It's completely recursive.
Exactly. In the valve, the intense pressure of the rushing water actually deforms the plastic melded material slightly. That microscopic deformation changes the water's flow path. Most basic simulations just assume the solid part stays perfectly rigid, like a block of steel. But because this is a polymer, it flexes under stress. They had to simulate that exact flex to get the geometry perfect.
So they could see on a screen, oh, if we flow water at this exact speed, the tip of the valve bends 1 millimeter to the left, and then they could fix the geometry on the computer before they ever spent money to cut a physical steel mold.
Yes, exactly. And doing that allowed them to completely eliminate dead zones and eddies in the fluid flow. You know how water kind of swirls backwards behind a large rock in the fast-moving river?
Yeah, the little mini whirlpools.
Those swirls are wasted kinetic energy. But in a car's cooling system, they're also dangerous for another reason: sediment.
Sediment. In a sealed car cooling system, where does that come from?
Over years of use, coolant can slowly degrade chemically. Tiny microscopic particles can form. Or you might just have residue left over from the original manufacturing process of the engine block. If you have a dead zone in your valve where the water just swirls around but doesn't actually move forward.
The gunk just builds up right there.
Exactly. It acts just like a sandbar in a river. Eventually, that gross buildup can physically clog the valve or chemically corrode the plastic material. By using those FSI simulations to ensure a perfectly smooth, continuous flow path, which the planar triangle design inherently helps with, you basically make the valve self-cleaning. The water constantly washes it.
Wow. So it lasts longer not just because the plastic itself is tough, but because the actual shape actively prevents gunk from accumulating.
Correct. It's just another vital layer of that robustness we talked about earlier.
Let's get into the hard specs for the gearheads listening. If I'm a systems engineer at Ford or Toyota, how do I actually integrate and talk to this valve?
It drops into the standard automotive electrical ecosystem perfectly. It communicates primarily on the LIN bus, which is a standard protocol local interconnect network. It's basically the nervous system of the car for non-critical body parts. But if you need it, you can also use CAN bus or standard PWM, and it runs on a standard 12-volt system, so no crazy high-voltage routing is needed.
And what about safety and durability? Because cars get wet, engine bays get incredibly dusty and hot.
It is fully rated for IP67 and IP69K.
Okay, IP69K. I know IP67 is like, I drop my phone in the toilet for a minute and it's fine. What on earth is 69K?
IP69K is hardcore. It means the component can withstand direct, high-pressure, high-temperature steam jets. Like, imagine if you were power washing the engine bay with industrial cleaning equipment from 2 inches away. It is extremely sealed and robust. And it targets ASIL B, which is a key automotive safety standard under the ISO 26262 framework.
Okay, so it's virtually indestructible. What about burst pressure?
It's rated to 12 bar. That is roughly 174 psi. For a lightweight plastic part, holding back 174 psi of boiling hot coolant is highly significant, and it can handle a steady flow rate of up to 75 liters per minute.
75 liters a minute. That is a massive amount of liquid moving through a tiny 145-gram piece of plastic.
It really is. And all of those specs lead us directly to the commercial value, which is really the bottom line, the so what for the entire automotive industry.
Right. Because why should the CEO of a major car company care about this? We talked about mitigating risk with Saint-Gobain's size earlier, but what about the actual vehicle design and the bottom line?
First is space saving. Modern EVs are packed incredibly tight. You want a big frunk for your groceries, you have the massive inverter, the bulky motor. Space is an absolute premium. Because the triangle valve is flat, it's a planar design, it slips into incredibly tight packaging spaces that a big, bulky, spherical ball valve simply cannot fit into.
It's like slipping a paperback book onto a crowded shelf versus trying to shove a soccer ball in there.
Exactly. The packaging engineers love it. Second is cost. Fewer parts inherently means it's cheaper and faster to assemble, but it also drastically simplifies the supply chain. For ball valve, you need a supplier for the ceramic disc, a supplier for the rubber O-rings, a supplier for the stamped metal housing. With this, you basically just need the molded polymer.
Right. Less tracking, less shipping, lower cost. And the third is weight.
Yes, a lighter car universally equals more range. Every single gram counts in the ongoing EV range wars.
It really does seem like they somehow hit the engineering trifecta here. It's cheaper to make, it's better at its job, and it's physically lighter.
It is a textbook, classic case of what happens when you finally stop endlessly iterating on an old design and instead completely rethink the fundamental physics. The automotive industry spent literally decades optimizing the ball valve, making the metal slightly better, polishing the sphere slightly smoother, finding slightly better rubber.
Polishing the cannonball, like you said.
Right. But EQYO stepped back, looked at the whole system and said, wait, why are we even using ball at all?
let's just try a triangle.
And that profound willingness to question the foundational geometry is what actually led to the breakdown of all those major pain points we discussed at the start of the show.
Let's circle back or, well, triangle back to those specific pain points for a minute. The range anxiety and the ultra-fast charging time.
Sure, if you have a thermal system that mechanically reacts faster because of that 50% driving angle reduction and flows significantly better thanks to the 45% less pressure drop, you can manage the massive heat spike of a 350 kilowatt fast charge much, much more aggressively.
So having better, faster thermal management literally enables that green 9-minute charge time to become a reality.
It is an absolute key enabler, yes. You
Right.
physically cannot have one without the other. You can build the biggest, most powerful charger in the world, but if the car's internal plumbing can't reject the heat fast enough, the car's computer will just throttle the charger down to protect the battery. This fast-acting triangle valve allows the car's brain to say, shut it down, give me full power.
And then the raw energy savings on the water pump and the tiny valve motor extend the driving range directly.
It's fascinating how all these highly disparate things connect in a complex system. We so often think of innovation as, a magical new battery chemistry or a crazy self-driving AI algorithm. But sometimes deep innovation is just making vastly better plumbing.
Highly sophisticated, mathematically optimized, atom manipulating plumbing.
Exactly. But it's true. It's the invisible, unglamorous infrastructure that makes the highly visible, cool features actually possible.
So this whole redefining efficiency title of their presentation, it really isn't just marketing fluff.
No, I don't think it is. It's a true synthesis. It is material science via the Meldon polymer plus mechanical innovation via the planar triangle plus digital design via the FSI simulation. You absolutely need all three legs of the stool or the 3 points of the triangle to make this leap work.
I see what you did there with the 3 points.
I really couldn't resist.
So EQIO is actively positioning this as the baseline solution for the next generation of xEVs.
Yes. They clearly see this as the elegant solution that finally solves the conflicting engineering goals of weight, cost, and performance simultaneously. Usually in engineering, you have to pick two. You know the saying, fast, cheap, good, pick two. They're confidently claiming they have unlocked all three with a simple geometry change.
And based on the hard data presented in the source material, the 58% energy save, the massive torque reduction, the improved flow, it seems like they actually have the receipts to back that bold claim up.
They certainly do. And coming from a company with the sheer scale and legacy of Saint-Gobain, the major automakers will absolutely listen.
So looking back at what we've covered, we have gone from a global chemical giant founded by a French king down to a microscopic polymer recipe over to a triangular geometric solution resulting in a 58% energy save on the component level, which then scales up to cure range anxiety. That is quite an intellectual journey.
It really is. And it's a brilliant reminder that the absolute biggest changes in an industry often come from rethinking the smallest, most ignored details.
Now, if people listening want to see this thing in action, because it is honestly kind of hard to visualize a flat triangle valve opening and closing a pipe just by listening to us talk about it, are there resources out there?
Yes, definitely. The presentation explicitly mentions that there are videos of the valve's inner workings and the simulated flow dynamics available online. I highly recommend checking YouTube or just going straight to eqio.com. Seeing the FSI flow simulation in motion really makes the whole concept click instantly.
And if there are any automotive engineers or product managers listening right now who are thinking, wow, I absolutely need this in my next vehicle platform, who do they actually call?
The man behind the entire presentation we reviewed today is Christian L. Haas, their product engineering manager. The source explicitly lists his contact info over at Saint-Gobain. He is definitely the guy you want to talk to.
Fantastic. You know, this whole deep dive has really left me with a lingering thought about the nature of simplicity in design.
Oh, yeah. Go on.
We so often think that advanced inherently means complex. You know, we want to add more sensors. We want to add more gears. We write millions of more lines of code. We constantly add things to solve our problems.
That is the ultimate human tendency. We love additive problem solving.
Exactly. But in this specific case, the most incredibly advanced, efficient solution was actually deleting parts. It was taking a heavy 10-part metal, ceramic, and rubber mess and brilliantly distilling it down into a 4-part plastic triangle. It just makes me wonder, where else in our technology, or honestly, even just in our daily lives, are we mindlessly using circles just because that's what we've always used?
That is a genuinely powerful question. I mean, the ball valve has been around since,
Yeah.
since forever. It
Yeah.
took someone completely stepping back and asking, Does it truly have to be a sphere to finally break through that decades-long efficiency plateau?
Exactly. Where else would a simple triangle work so much better if we just stopped trying to aggressively polish the sphere?
That is definitely something for everyone to mull over today. Whether you are an engineer designing next-gen spacecraft or you're just trying to reorganize your kitchen cabinets, look for the radical simplification that relies on better fundamental geometry, not just applying more force.
I love that. Keep looking for the triangles in a world of spheres.
I think that is the absolute perfect note to end on.
Thanks for listening to the deep dive, everyone. We will catch you on the next one.